Okay, one of the last problems from Chapter 13 on gas laws is a gas law reaction. So we're dealing with a reaction that includes the ideal gas law. Basically, you have gases that react to form lots of things, including gases. So the things to remember is that this time, whenever we do this gas law reaction, we're going to need an ice table because we have to look at the gas products as well as what happens to the gas reactants. Gas reactant pile goes down, the gas product pile goes up. Okay, so here's our example problem. This is very much like the other problems in 13D. Hit pause, see if you can do it. Remember, we went through this in class. Hopefully you're good at it now. And then we'll take a look at how to work it. Okay, hit pause. Alright, you're back. You've pounded through. Hopefully you have something close to the right answer or the right answer, and then we'll see what to do. If you get stuck at any one spot, try to see how I did it. So because we have a reaction, combustion reaction, you have to write out the reaction first, the products and reactants. Okay, so that's first. C2, H2 reacts with O2. And notice that everything is a gas, so we don't have to worry about that part. Goes to carbon dioxide and water. Alright, so we have to have a balanced equation. So we'd start maybe with this one. If that's a 1, that would be a 2. If there's 2 of these, then that would be a 1. 1, 2, 3, 4, oxygen's 5, then that won't work. So let's double this many, which means we need 4 carbon dioxides. That means 4 water, so that has to be a 2. And that's 8, 9, 10 oxygen, so that would be a 5. Okay, 2 to 5 to 4 to 2 is the ratio. Okay, now I told you earlier that you're going to need an ice table, and we'll look at why. Initial, change, end. Okay, now why exactly do we know that we need an ice table? Well, let's think about what we have so far. And just think about the words to the problem. Every time you have a reaction, this is going to happen. If it's a gas law problem from exercise 13, gas law reaction, you're going to have to do this. Let's think about this. A 44.4 liter closed steel can contains this much gas and this much gas at this temperature and this pressure, and after the reaction the temperature goes up. What's the new pressure? Well, I hope you recognize here that this is a P1 V1 over P2 V2 problem, right? Because we got 2 different sets of conditions here. Cold temperature, low pressure, hot temperature, want to know the new pressure. Okay, so every time you have this kind of setup, you want to cross out things that you know don't change. R never changes, so it looks like a 1 and it cancels out. A closed steel can, no matter what the volume is not going to change its volume. So those cancel out. It's clear that this is P1 and this is T1, so we know P1 and T1. They give us a T2 and they want to know what P2 is. So we're going to try to solve for P2. So the big question is about N1 and N2. So let's fill in what we know and see what we know. Alright. Initial means something, right? Okay. So we started with 3.7 moles of the C2H2, that's acetylene, and 9.9 of the oxygen. And notice that we don't make the CO2 and the H2O until after reaction, which means we start with none. If it said that there was carbon dioxide and water in the gaseous form in the can, we'd have to include those, but it doesn't have any. So you need to have the understanding that the initial added up is N1. That's all the gases that are in that can that begin with at that temperature to give it that pressure. So we have to add 3.7 and 9.9, and when we do, N1 is 13.6 moles. Okay, so that's something that we know as well. N2, well, N2 is going to be the moles of gas with the new temperature and pressure, or in other words, the moles of gas that we have at the end. And the only way we can figure out what N2 is by going through the process of the reaction, determining what the limiting reagent is, how much is left over of the excess reagent, and how much of the product is made. Now remember, the change for the reactants, the reactant piles always go down, right? But this time we have to keep track of the product piles, and they always get bigger when a reaction occurs. Okay? So we just have to figure out what these changes are. And we have to go through a decision-making process to try to figure out which of these is the limiting reagent, right? Either all of this is going to get used up and we'll end up with 0, or all of this is going to get used up and we end up with 0. There are two calculations that you could do to easily figure it out, and this is just basically comparing the two reactants. We'll do both possibilities to look at the logic, but you only have to do one. It's all about figuring out what the limiting reagent is. Okay, because once you figure out what the limiting reagent is, that will tell you the changes. Okay, using that number. Alright, so we're going to do them over here. 3.7. This is A. This is an A calculation. We'll do A or B. 3.7 moles of C2H2. And we're going to look at the 5:2 ratio. So that gives us a value, and what is that value? That value is 3.7 times 5 divided by 2, or 9.25, 9.3. So what exactly does that mean? That is the 9.3 moles of O2 needed. Okay? That's the amount needed to react all C2H2. Okay? Now, here's the big question. Did we have enough O2 at the start? This is how much we know we need. Did we have enough at the start? So you need to take a look. Yes, we did. More than enough. Okay? So, if you decide that there's more than enough O2, that means O2 is excess, right? That's what more than enough means. And if O2 is excess, then C2H2 is the limiting reagent. Okay? So, either that is true. Hey, that's Bean. Everybody say hello to Bean. Goodbye, Bean. Okay, so that's the decision-making process that you go if you decided to look at 3.7 moles of C2H2. What if we had started to decide to look at 9.9 moles of O2? Well, here's how that decision would go. You'd look at the ratio. Shh. Now we look at the ratio, and we would find .9 times 2 divided by 5 is 3.96, or 4.0 moles of C2H2 needed to react all the O2, right? But then you have to ask the question, did we have enough? Did we have enough at the start? Did we have enough C2H2 at the start to react all the O2? And if you look, we did not. No. Only 3.7 moles. So what does that say? Well, what that says, I think, should be pretty obvious. It should tell you, without question, as I go to get a pencil, therefore, I think it's pretty obvious that C2H2 runs out. Therefore, limiting reagent. Okay? And your job is to find out which is the limiting reagent, because once you do that, you use 3.7 moles C2H2 for all the changes. Calculations. Alright, so let's give those a try. Well, first off, what's the change in the C2H2? If it's the limiting reagent, then there's none, right? And if the C2H2 reacts, 9.3 moles of O2 react. We already figured those out. So when you do that subtraction, there's 0.6 moles that are left. Okay, I've got a cat that's trying to sabotage, and I will not let it happen. We are going to pound through here. I'm not going to be distracted. I am not an ADD teacher. He's back. He's back. I'm not going to let him out of here, dude. Hit the road, Jack. Hit the road, Bean. Alright, so let's figure out how many moles of C2, or carbon dioxide, and how many moles of water will form if 3.7 moles of C2H2 reacts. And that's not hard. 3.7 moles C2H2, 4 moles CO2, 2 moles C2H2. It's just double. That's 7.4 moles of CO2 forms. That's where that goes, and that adds up there. And then we do one more calculation down here, and that's 3.7 moles of the acetylene, and it's a 2-to-2 ratio for the water. So it's 3.7 moles of water vapor forms. Okay, 3.7, 3.7. Alright. There is no other way to get this value, but this, as you can see, are the moles of gas at the end. which is what N2 is. No C2H2 is left, but we've got a little bit of oxygen and then carbon dioxide and water. So whenever we add 3.7, 7.4, and 0.6, we get 11.7 moles of N2 at the end. Now we know everything, so let's go back and solve. So, algebraically, we know, after letting all the crosses canceled out go, that we have P1 over P2 equals N1 T1 over N2 T2, right? Cross multiply through the equal sign gives us P1 N2 T2 is equal to P2 N1 T1. Good. We're solving for P2. Divide those sides by N1 T1. P2 is equal to P1 N2 T2 over N1 T1. Plug and chug. Pressure 1. All the way back over here, 1.09 atmosphere. N2, we just figured it out, 11.7 moles. T2 is the second temperature, which is 947 plus 273. Gotta convert. 1220, right? Okay, Kelvin. And then we're going to divide by N1, 13.6 moles. And T1, which is 21 plus 273. T1 is 273 plus 21, 294. Okay, we've converted to Kelvin. Moles cancel, we're left with pressure. 3 sig figs in our answer. Now this is sort of interesting because the temperature went from 21 degrees C all the way up to 800 or 947. From 294 up to 1220, we would expect that would result in a higher pressure. However, the number of moles of gas went down from 13.6 down to 11.7, so that would mean a lower pressure. So we'll see which process took precedence here, whether the temperature or the moles of gas predominates. Divided by 13.6 divided by 294 equals new pressure 3.89 atmospheres, 3 sig figs. Okay, so the pressure went up almost 4 times, and I think it's because the temperature rise was really huge. Okay, so the key to this is determining what N1 is. That's really what's given, but there's no other way to get N2. After that, it's just a simple algebra problem. All right, have at it. Good luck.